Hey everybody, this is Victoria and Corey. We are the Professors DuBois, and today we're going to be talking about acid-base reactions.
All right, so if we're going to talk about acid-base reactions, we have to know or be able to identify what an acid and a base is. So let's start with acids. There's actually a couple different definitions of acids, and the one definition that we really focus on in general chemistry is the Bronsted-Lowry definition. And by definition, an acid is a proton donor. And a proton is represented by the H+. Now, if this seems a little bit funny, you could kind of back up a little bit and think about hydrogen. What is in the nucleus of a hydrogen atom? So we have one proton. Well, if we also have one electron in this atom, but if we lose the electron, we would get the +1 charge, and all we have left is a proton. So a proton is a hydrogen ion, the H+ ion. So by this definition, acids have to have a hydrogen.
Yep.
And they're usually written out front.
Usually. All right, so this is a little bit out of the kind of sequence with what we're talking about here, but it's really important, so we wanted to put that right up front. All acids are soluble, so you're not going to use your solubility table of ionic substances to determine if an acid is soluble or not. And that gets really important with our aqueous chemistry that we're going to be working with in this chapter. So all acids are soluble, but we can classify acids as monoprotic, diprotic, you might see polyprotic as well. And that's telling you that how many protons can be donated. Polyprotic. So monoprotic means one proton. So that means we can have one donatable proton from the molecule. So in our example here is we have this one HCl. Diprotic acids can donate two from their molecule. Here's an example of sulfuric acid, has two hydrogens that it can donate. Polyprotic just means many. So you might have more than two. Our example here might be H3PO4, where we have three donatable hydrogens. Not all hydrogens are donatable, and that, especially when you get into organic acids, some of those hydrogens can't come off. So these are, you may see more hydrogens in the molecule, but only one can be donated. There's an example right here.
This is acetic acid. It's a weak acid. It's written in a couple different forms. We chose to put the hydrogen out front here to be consistent with the hydrogen coming first. But we have an acid and we have a base. We didn't really talk about the bases too much, but bases often have a hydroxide component to them, but not all of them do. We also have a lot of bases that have nitrogen with them, like ammonia. So we have KOH, which is a base, potassium hydroxide, and the weak acid. And really what's going on here is this acid is donating that proton. And there's just one, this is a monoprotic acid. Even though there's additional hydrogens in there, the ones that are bonded to the carbon are not going to be donatable. So it donates its proton to the base, and we end up forming water and potassium acetate, and we can predict these products very similar or just like a double displacement type reaction.
So when we have an acid-base reaction, we always have one thing that's donating its hydrogen ion. So we can call this the acid. Whatever's receiving the proton is the base. And when we have a strong acid and a strong base reacting, we produce water and salt. And that's why we call it a neutralization reaction. So we have something that was a very low pH combining with something that's very high pH. And it's okay if you don't know pH yet, we're going to get to that. But when we combine them and we produce something that's neutral, we have neutral salt and a neutral water, it's a neutralization reaction. So you might see this as an acid-base reaction or a neutralization reaction. A salt is defined as an ionic compound, not necessarily table salt, which is what NaCl is.
We got a reaction here. So I noticed that this compound has an H at the beginning. It's this is an acid. It's going to donate that proton to the other compound. It's got a hydroxide. That kind of jumps out at me as being a base. We can predict these products by doing a double displacement type arrangement. So the H is going with the OH to form water, which is liquid. And the barium is going to combine with the phosphate. And this one's going to be a little bit tricky to make neutral. We're going to need 3 bariums and 2 phosphates to make a neutral compound. So that has no charge on it. Now, the next step is to figure out the state. Now, this barium phosphate, I would go to my solubility chart. I would look for the phosphates. Most of those phosphates are insoluble. They don't dissolve well. I look to the exceptions. Barium, not an exception. This is a solid. It's insoluble. We write S for solid. So we could call this an acid-base reaction. We could call this a precipitation reaction.
And I'm going to call it an unbalanced reaction.
Let's balance this reaction.
We've got 3 bariums over here, and I only have 1 over here. So I'm going to start with doing a 3 in front of that. That means that I have 3 hydroxides. I need 3 hydroxides with 3 hydrogens to make 3 waters. And we can balance our polyatomic ions with just as a polyatomic ion. But look at this. I have 1 phosphate over here and 2 over here. Uh-oh. Uh-oh. That means that everything is going to be off. So I'm going to double my phosphates. Now I have 6 hydrogens. I need 6 hydroxides to make...
Hold on, no.
What'd I do?
You've got 2 hydroxides there, so 2 times 3 was 6.
Oh, I was already there. Thank you. 3 makes 6 hydroxides. So I have 6 waters. Am I good now? 3 bariums, 3 bariums. 2 phosphates, 2 phosphates. 6 hydrogens with 6 hydroxides to make 6 waters.
And when I balance, I don't do the hydrogens to hydroxides to make waters. I kind of brute force count my hydrogens and count my oxygens.
Both work.
It's slower, but it works better for me.
All right, here's some practice for you. Pause the video and try these out.
Let me just give a little hint here that in that first reaction, the second reactant is acetic acid. So that is a weak acid, and it's the way it's written here, the donatable hydrogen is right there. So that's where you would break that apart. So you'd have the proton and the acetate ion. Hopefully that'll help you get started.
Here comes the answers. All right.
I noticed you wrote HOH there instead of H2O.
Yeah, look at that. You can represent water in a couple different ways. They're the same. Same thing. Hopefully this helped. Appreciate you tuning in. And come back to the Professor Du Bois channel anytime you need help with chemistry.
Bye.